So here we are solving a similar problem to homework 2, problem 8. We are given a ball moving in 2 dimensions, x and y, with a constant acceleration. We don't know what that acceleration is, but part A is going to have us find it. We're given the ijk notation for vector, for the velocity vector, that v1 and v2. So we can rewrite that. We're going to want to make sure that velocity vector is written in a way we can understand. We have 6 comma -3. And so we're just pulling that from the v1 equation. And I prefer this vector format over the ijk notation, but both are acceptable. And we find v2 to be 7 comma 3. And both of those are in meters per second. And it is important to make sure you write your units down. And so here is t equals 0. And we find at v2, t equals 5. Those are both in seconds. So part A says find the acceleration of the ball, express in component form as well as magnitude angle form. So how do we define acceleration for this problem? Well, if you remember from the fundamental definition of acceleration, acceleration is the derivative of velocity with respect to time. But not only that, it is the change in velocity over a change in time. Right, we can't really take the derivative of 2 points, right? That's a little tricky. What we can do is express the derivative as the change in velocity by the change in time. So how do we know what the change in velocity is? Well, why don't we express the change in velocity as v2 minus v1? If you remember, delta is just the final minus initial, right? So our final is v2 minus our initial of v1 over, well, we have 5 seconds minus 0. So our delta t is 5. And now we can just go ahead and plug in those vectors. We don't even have to change them or write them in a different form. We can just use them directly in this algebraic expression. So what is the difference of these two vectors? Well, we look at the x component first on its own, and then the y component on its own. And so we're looking at 7 minus 6, which is just 1. And then we're looking at 3 minus -3. That's going to give us a positive 6. And then we keep that all over 5. The next step is to take that 5 and distribute that to every term in that vector. So we have 1 divided by 5, comma 6 divided by 5. And so this is our acceleration in component form, right? It wasn't that bad to find, as long as we understand that acceleration is the change in velocity over a change in time, and that we can do algebra to this velocity. We don't have to get it out of vector form and then bring it back in. We can just keep it in vector form. But that's not all we have to do for part A. We have to also find the magnitude angle form. And if you remember, the magnitude is the square root of the x component squared plus the y component squared. And so the magnitude of this vector, we're going to say the magnitude of A is going to be the square root of 1/5 squared plus 6 over 5 squared. And plugging into the calculator, we get 1.217. What are the units of acceleration? Well, they are meters per second squared. We're going to go up and put those back there too. And we found the magnitude, but we don't have the direction, right? Well, if we were to plot this vector on a xy graph, positive x, positive y being in their normal directions, well, we would have an x of 1/5 and a y of 6 over 5. Well, we found the magnitude to be 1.217. And it's nice to just have a decimal for that magnitude. The form doesn't really matter. Now we have to find theta. Well, using trig, we know that tangent theta is equal to opposite over adjacent. And so we can apply that to this triangle. And well, we can take the tangent inverse of this equation. And so we have theta equals tangent inverse of opposite over adjacent, which is equal to tangent inverse. Our opposite is going to be 6 over 5 divided by our adjacent of 1 over 5. And so that gives us an angle of, that gives us 80.5 degrees. And so normally you will rewrite your magnitude and direction and say 1.217 meters per second squared at 80.5 degrees north of east, right? East is our baseline, and we are going a little bit north of the east direction. And that is the typical way of expressing your answer, but as long as you convey an accurate direction and magnitude, your answer will be right. All right, so now that we've done part A, we have to find the coordinates of the ball at any time t. Well, that's a little bit trickier, right? We know, how do we express the coordinates, right? Well, the coordinates are in x and y position. So, well, we're in a kinematics unit. We know we have these kinematic equations. Why don't we use position equals initial position plus initial velocity times time plus 1/2 at squared. And we can actually change that into the y form as well and use that for our y-axis. And it's just a little important to notice that our v initial and our a are also respective to the y or x axis, so we don't really want to get those confused. Right, we need to make sure we use the correct acceleration or velocity component. So let's work in the x direction, or the x-axis component area. Work in x first. So what we have is initial position first. Well, we don't really have any position reference for this problem, right? We just have velocity and acceleration. So our initial position, we're just going to use 0. And that's sort of the default. So we're just going to leave that term off. I'm just going to strike that to 0. Now we have the initial velocity in the x direction. Well, if we go back to the question, well, v1 was our initial velocity. And we had 6 and -3. So we can go in and say that v initial in the x direction was 6 times time. And in the y direction, we had a v initial of 3 times time. And now we're on to that second term, 1/2 at squared. Well, we found acceleration in its vector form to be 1/5, 6 over 5. So we can actually use a in the x direction is 1/5 times t squared. And in the y direction, it was 6 over 5 times t squared. Write that squared up there. And so these two equations, just as they are right now, accurately express the position as a function of t. All we're going to do here is just simplify the expression a little bit, make it look a little bit pretty. 3t plus, we have 6 over 10, so that's 3/5 t squared. But when we look at the question, just to make sure we format our answer correctly, it says find the coordinates of the ball at any point in time t. We have x, we have y. Now we just want to put them together for our final answer. And so we're going to say the point xy is, and so we can just take that equation for the x and y component and plug it in to our x and y point. And so we don't actually want to write this as a vector. We want to keep this in parentheses because we are just expressing a point and not a vector. That's the important thing to distinguish, is that we represent a point with parentheses. And we are representing the point that the object is at a given t. And so here we have expressed the position as a function of time. And that answers part B.